Hello everyone, welcome you all in a video lecture series related to heat and mass transfer. Today we are going to start our new chapter named as finite differential application in heat conduction and convection. So university has provided the syllabus under this particular chapter is nothing but introduction to finite difference, then finite difference methods for solving conduction and convection problems, then one-dimensional steady-state heat conduction, boundary condition, and finite difference application in convection heat transfer introduction only. So, what is meant by finite difference application? Okay, and what is meant by finite difference method? So that we need to understand. While solving different kinds of a problem related to convection and conduction, we come to know that this problem solution or the calculation very tedious one. So for that purpose and at the end of the solution, there is no guarantee to achieve the correct solution for that particular problem. And if the conditions, boundary conditions are typical one, then it is very difficult to solve the problem. So in order to solve problems which includes complicated geometries as well as boundary condition, the analytical method becomes inadequate to give the exact solution. So in order to have a solution of such a problems, one can use numerical methods. The numerical methods for solving different equations are based on replacing differential equations by algebraic equations, and by solving this algebraic equation using numerical methods, one can have exact solution for such a problems. In the case of popular finite differential method, this is done by replacing the derivatives by differences, and reasonable accuracy result can be obtained. So generally the problems in a heat exchanger, in a heat transfer, the problems related to heat and mass transfer can be solved by using these four methods or four approaches. The first one is finite difference method, second one is finite element method, third one is boundary element method, and fourth one is energy balance or control volume method. Now all these methods are using numerical methods to get the solution. So generally use numerical methods for solving the obtained formulation by using four methods are okay. So these above four methods are using the numerical methods. So which are that numerical methods? Actually you learn that numerical methods in mathematics. So the first one is a relaxation method, second one is a direct method. In a direct method there are two methods. First one is a Gauss elimination, second one is inversion matrix method, and third one is the iterative method. The iterative method in that Gauss-Seidel, Gauss quadrature, Runge-Kutta method, etc. methods are involved. So these methods can be used to find out the solution, exact solution by using these four approaches. Now the finite differential method. So actually the derivatives are the building blocks of a differential equation. So in a finite differential method, derivative terms are replaced by finite differences. To understand this, let us consider one example. Here the function f of x, let us consider the temperature profile. Okay, so this is the temperature graph with respect to some independent variable. So we are going to consider that f of x is a function of x. So f is a function and it is depend on a x variable. So as x goes on varying, this function also goes on changing, or its value also goes on changing. So f is a function which is depends on x, and for that purpose we are writing f of x. Okay, so function f is depend on x, and we are getting the profile for that particular function. Okay, let us consider the temperature is a function. Okay, and it is depends on a distance. So according to distance, or the temperature goes on varying. Okay, now if you want to plot the or if you want to get the get the delta f divided by delta x, that is nothing but the slope of this particular graph. If you want to get the slope of this particular graph, then we have to take the first differential. Okay, that is nothing but differential of x with respect to x, which will provide us the graph slope at this particular point. Okay, so as here we have considering that for taking the slope, the two quantities on x-axis we have taken. The first point we have considered as x, and the second one is x plus delta x. So the value corresponding to the x point on this particular plot we have to consider as f of x, and the value corresponding to this particular point x plus delta x on the graph or on the profile we have to consider as a f of x plus delta x, as f is a function of x. So we have already stated the first derivative of f of x at a point is equivalent to the slope of the line tangent to the curve at that point, and is defined as, okay, so it is defined as the differential of f of x with respect to dx is equal to limit divided by delta x tends to 0, delta f, that is the difference in y-axis values, and divided by delta x, that is the difference in x-axis values. So we'll get the equation as limit delta x tends to 0 of f of the equation f of x plus delta x minus f of x divided by delta x. Okay, that is the change in value of, or difference in value of y-axis divided by difference in value of x-axis. Okay, so here the difference in value of x-axis will be x plus delta x minus x, will give us a delta x only, and difference in value of y-axis will f of x plus delta x minus f of x, that we have written over here. Okay, so we can say that from this particular equation that the differentiation of function with respect to x is the ratio of the increment in delta f of the function to the increment in delta x of the independent variable at delta x tends to 0. Now if we don't take the indicated limits, that is nothing but delta x tends to 0, we will have the following approximate relation for the derivative. So that is nothing but from this particular equation, the differentiation of f of x divided by differentiation of f of x with respect to x will be equal to f of x plus delta x minus f of x divided by delta x. This approximate expression of the derivative in terms of differences is the finite difference form of the first derivative. Now there is another one method to get this equation. So method 2 is the above equation also can be obtained by writing Taylor series expansion of the function f about the point x. Okay, so by Taylor series also we can get this particular equation. This equation we can get by using the Taylor series also, expansion of a Taylor series. So the expansion of f of x plus delta x by Taylor series is given as f of x plus delta x multiplied by differentiation of f of x with respect to x plus delta x square divided by 2, and second differentiation of f of x divided by dx square, and so on. Now here we'll get above equation by neglecting the higher order derivative. Higher order derivative means what? We have to take the terms up to the first derivative only, and remaining further expansion we have to neglect from this particular equation. So therefore we will get the equation f of x plus delta x is equal to f of x plus delta x multiplied by df of x divided by dx. So if you rearrange the term, if you shift this f of x on this side and divided by delta x, then we will get the equation in the form of differentiation of f of x divided by dx. So differentiation of f of x with respect to x will be equal to f of x plus delta x minus f of x whole divided by delta x. So we will get the same equation as that of above. So this equation once again we can get by using the Taylor series. Now third point of this chapter is finite differential method for solving conduction problem and the boundary convection problem also. So for that purpose here we have considered the steady state one-dimensional heat transfer in a plane wall of a thickness L with heat generation and constant thermal conductivity K. So this is the wall and whose thickness we have to consider as L. Okay, its thickness is L. Now this wall we have divided into m equal thicknesses. So each having thickness of L divided by m. Okay, so there are we have divided from 0 to m. Okay, total m equal parts we have given to this particular wall. So it is equal to 0, 1, 2, m minus 1, m plus 1. So any point on or any dividation we have provided the m significance, and previous to that particular m we have given the significance as m minus 1, and next to that particular dividation or the part of that particular wall we have provided m plus 1. Okay, now this is the nodes 1, 0, 1, 2, m minus 1, m plus 1 up to m. These are the nodes. It is called as a nodes. Okay, now here we have to remember that the property of one node, okay, if you consider the property of a node m, it will be same up to m minus 1. Okay, and it will be same up to m plus 1. So influence of m is up to half of the thickness of a node succeeding and preceding. Okay, so the wall is subdivided into m sections of equal thicknesses. Okay, so m section we have divided the wall in m sections. The thickness of each section will be considered as a delta x. Okay, so one the distance between two nodes, that is nothing but the thickness of a section, so that will be considered as a delta x, and its thickness will be L divided by m, because the wall thickness is L and we have divided that particular wall thickness into m section. So one section thickness will be considered as a delta x is equal to L divided by m in the x direction, in this x direction. So 0 we have provided here. So positive x direction, in a positive x direction we have provided the numbering. Okay, now the 0, 1, 2, 3, m minus 1, m plus 1 up to m, capital M, called the node points. Now consider that the heat is transforming to this particular node from the left side. We have considered it as a q dash x amount of heat will be transferred to this particular node, and the q dash g amount of heat is generated inside that particular element, and q dash x plus delta x, q dash suffix x plus delta x amount of heat is transferred by this particular m element to another element. Okay, now this will be consideration. So consider q dash x is equal to amount of heat conducted to the node from the left side, and q dash j amount of heat generated within the node. Then q dash x plus d delta x is equal to amount of heat conducted out of the node to the right side. So by energy balance equation, we can write the equation as q dash x minus q dash x plus delta x plus q dash g is equal to increment in internal energy of a element divided by delta is equal to 0. Okay, here we are considering that whatever the energy received by the element, that much amount of energy will be transferred to the next element. So the increment in energy of internal energy of the element with respect to change in time will be considered as a 0. Now here q dash g, okay, that is nothing but heat generated per unit time by the element is equal to q suffix g, small q suffix g multiplied by v, where small q suffix g is nothing but heat generated per unit volume per unit time, and multiply by volume we will get the heat generated per second only. Okay, so volume is nothing but what? The surface area multiplied by thickness. So q dash g is equal to q suffix g multiplied by area into delta x. For the one element, the thickness we have considered that delta x. Okay, or for one section we have considered the thickness delta x, and A is the perpendicular surface area available for the conduction. So according to Fourier's law, we know that according to Fourier's law, q is given as k multiplied by A multiplied by T1 minus T2. So T1 is nothing but initial temperature minus T2 is nothing but the present temperature or the next temperature. Okay, so here in case of q dash x we have considered over here, that is nothing but energy given to the node M or the section which consists of a node M. So q dash x, so the initial temperature will be considered for the node point M minus 1, and the next temperature will be considered for the node point M. So and the thickness will be considered as a delta x. So we will get the equation for q dash x is equal to thermal conductivity K multiplied by perpendicular surface area A. Now into bracket, the initial temperature will be considered for the previous node point, that is T suffix M minus 1, minus the next temperature difference we have to consider for the M node point, so it will be equal to T suffix M whole divided by thickness. The thickness will be considered as a delta x. Now the next we have to consider the q dash x plus delta x. Okay, so heat given by this element to the next element. Okay, so initial temperature in that case, initial temperature here, so this element or this section is giving the heat to the another section. So next temperature we have to consider for M plus 1 node, and the previous temperature we have to consider for M. Okay, or the initial temperature we have to consider for the node point M, and the next temperature we have to consider for at node point M plus 1. So our heat transfer by conduction, that is the Fourier equation for q dash x plus delta x, becomes k multiplied by A into bracket initial temperature is T suffix M minus next temperature at a node point M plus 1, that is T M plus 1 whole divided by thickness delta x. Now equation 1, that is the energy balance equation, becomes k multiplied by A we have taken common, then into bracket T suffix M minus 1 minus T suffix M divided by delta x minus T suffix M minus T suffix M plus 1 divided by delta x, bracket complete, plus qg multiplied by delta x multiplied by A. Now next we have to divide k multiply A throughout the equation. So we will get the equation as this delta x base is common, so we can add this to or we can subtract these two numerators. Okay, so we will get the equation t suffix m minus 1 minus t suffix m minus t suffix m plus t suffix m plus 1 whole divided by delta x plus qg divided by k multiplied by delta x is equal to 0. Now next we have to divide by delta x throughout. So then we will get the equation t suffix m minus 1 minus 2 multiplied by t suffix m plus t suffix m plus 1 divided by delta x square plus qg divided by k is equal to 0. Now this is the general equation, we can say that, for the general heat conduction equation in a differential format for the one-dimensional steady state heat transfer. Okay, so for combination of conduction and convection, the one-dimensional steady state finite differential equation becomes, now if you say that at the boundary of the wall there is a convection heat transfer from surrounding to the surface or from the surface to the surrounding, in that case we have to take the consideration for the convection heat transfer. So Newton's law of cooling, we know that, so just add that particular convection heat transfer in a conduction heat transfer. So we will get the equation for the combination of conduction and convection. So we will get the equation H multiplied by A suffix S multiplied by Ts minus Ta plus Tm minus 1 minus 2 T suffix m plus T suffix m plus 1 divided by delta x square plus Qg divided by K is equal to 0, where H is nothing but heat transfer coefficient and A suffix S is the surface area available for the convection heat transfer, T suffix S is the surface temperature, and T suffix A is the ambient air temperature or surrounding fluid temperature. Now for radiation and conduction, in the same manner we have to consider the heat transfer by radiation, and in that case we have to consider this particular radiation equation, a radiation heat transfer equation, that is nothing but sigma multiplied by A multiplied by eta into bracket Ts raised to 4 minus Ta raised to 4. In this equation the sigma is Stefan-Boltzmann constant, eta is nothing but radiation effectiveness, that is emissivity, and Qg is heat transfer rate per unit volume per unit time. So then for the combination of conduction, convection and radiation, we can write the equation as T suffix m minus 1 minus 2 T suffix m plus T suffix m plus 1 whole divided by delta x square plus Qg divided by K. This is the conduction heat transfer plus H multiplied by A suffix S into bracket Ts minus Ta, which is the convection heat transfer, plus radiation heat transfer sigma multiplied by A multiplied by eta into bracket T suffix S raised to 4 minus T suffix A raised to 4, that is the radiation heat transfer. Now the next point of this chapter is one-dimensional steady state conduction boundary conditions. Mathematically the expression of the thermal conditions at the boundaries are called the boundary conditions. Okay, the mathematical expression at the boundaries under control volume, such expressions are called as a boundary condition. So boundary condition most commonly encountered in a practice are specified in the specified temperature, specified heat flux, convection and radiation boundary condition. So the specified temperature boundary condition is the most simplest boundary condition to deal with for one-dimensional heat transfer through a plane wall of a thickness L. The specified temperature boundary condition on both the left and right surfaces can be expressed as T when temperature when the thickness is 0 or at the starting of the wall, that is nothing but 0 distance, is equal to T naught, T suffix naught. So we have to specify that particular value at the inlet of the wall and at the exit of the wall or at the another surface of the wall, that is nothing but when thickness is equal to L. At that time we have to consider the node point as M. Okay, So zero node point, this is the zero at a zero node point, and this is when we have considered the another surface node point as a m, so that t suffix m will be specified value. Okay, so that will be the specified temperature boundary condition. In that we have to specify the two surface temperatures, or the nodes on a two surface, we have to specify the temperature of that particular two nodes. Then when other boundary conditions such as the specific heat flux, convection, radiation, and combined convection radiation conditions are specified at the boundaries, the finite difference at the boundary can be obtained by writing an energy balance on the volume element at that particular boundary. That is nothing but what, when there is a convection boundary conditions, we have to provide radiation boundary condition, we have to provide, or heat flux boundary condition we have to provide. In that case, we have to write the energy balance equation for that particular boundary node, and that energy balance equation is in the format of summation of all the sides heat transfer rate plus heat generation by the element is equal to 0. Okay, so this is about the chapter number 8. We'll stop here. Thank you.